Go. Okay, so welcome.
All right.
Today we are going to learn about linear functions. All right. So let's just start off with a simple, relatable example. Right. We'll just say that we're in a race and we're going to race in our little race car, and we're going to travel at a speed of 50 miles per hour. Not particularly fast, but we are going to cheat. We're going to have a helicopter drop us off 50 miles ahead. Before the race even begins, we're already 50 miles ahead. Who needs a fast car when we can just cheat? Okay, so let's make a little cheat chart with the time in hours and the distance we have traveled, how far away we are in miles, right? So after 0 hours, right, as soon as the referee goes, bang, go, how far away are we?
We're at 60 at that point.
Very good. After 1 hour, remember we're traveling at 50 miles per hour, how far away are we going to be?
Already at 60, 1 hour
Plus,
puts us 50. That puts us at what? 110 at that point?
yeah, very good.
Okay.
Yeah, I'm sure you detect the pattern now. You add 50. So after 2 hours, how far away are we?
We'd be at 110. We'd be at 170 at that point.
Close, 160.
Yeah. No, it's been a long time, brother.
After 3 hours, we'd be
At 210.
very good. Now here's where it gets difficult. How about after 3 hours? So let's take a moment and probably, kind of explain what just happened, right? I'm sure you noticed that at every step, you added 50 to get to the new value. Now you started off with just plain old 60. In order to get 110 miles after 1 hour, you added 50. Now you added another 50 to get to the distance of 160 miles after 2 hours. Notice that you added 50 twice.
Yeah.
When you add the same number twice, it's the same as
a multiplication, you're basically just doing time times 2. Yeah.
Times 2. Very good. Can you predict what this is going to look like after 3 hours?
50 times 3 plus the 60. Yeah.
Very good. Now going back over here, any number times 1 is itself. Now look at this pattern here. By observing this pattern, can you kind of outline what the distance would look like after T hours?
It'd be whatever the distance is equals 50 times T plus the 5th or plus the 60, right?
Very, very good. That's excellent. That's a huge achievement. Congratulations.
Okay.
Pat yourself on the back. Good job. Congratulations, because that right there is a linear function. You just constructed your first linear function. You should be very, very proud of yourself. All right. Now let's rewrite this linear function here. And takes a little bit of time to explain some of these numbers. So 50, that was the what? Where did the 50 come from?
That's the constant, because that's your rate of speed in this case.
Yeah, that's speed. The 60, what number does that represent? What?
That's the distance that's a guarantee that you've already traveled.
Yeah, already. Yeah, okay, already ahead, let's say.
Okay, yeah.
The cheating distance. And this is, of course, the variable. Variable. In this case, it represents time in hours. Now, more generally, speed represents a rate of change.
Okay.
this already ahead distance, if you want to sound fancy and intimidate your enemies and impress your friends, is called the initial value. What you started with, right? The starting value. Sometimes it's better to just call it the starting value. But if you want to intimidate your enemies, initial value. So this actually gives you an idea of the general structure of any linear function. It's always going to be the rate of change times the variable plus the initial value. So this right here is the general structure of all linear functions. It's super important, worth writing down.
Oh, for sure, man.
All right. So with this in mind, let's do one quick example. So this is the example from the notes. Hopefully you read them ahead of time. So you're at a party, right? And damn, man, we need to go get more beer, bro. And you have a keg that's has a capacity of 15.5 gallons, and it needs to be refilled. And it just so happens that you go to the store and the faucet at the store pours beer out at the rate of 0.75 gallons per minute. Fortunately for you, there's still half a gallon, 0.5 gallons left in the keg. All right. So the first order of business that we want to commit is we want to build or construct a linear function for this situation for the volume of beer after t minutes. Okay, so probably important to outline some important steps. The first step you want to look for is you want to look for a rate of change. Which number in this paragraph represents a rate of change?
This is going to be the the pouring.
The pouring, and how fast is it pouring?
It's pouring at 0.75 GPM. Yeah.
Very good, perfect. So 0.75 gallons per minute. Yeah, very good. So that's the first order of business. Second order of business is now you have to find an initial value, if there is an initial value.
The initial is going to be either the 0.5 that's left or the capacity of 15.5. I guess it's probably the 0.5 that's left.
Very good, very good. And the reason for that is because you're trying to fill it up.
Correct, yeah.
And since you're trying to fill it up, you already have 0.5 that's already filled as you're trying to fill it up. Very good, very good, very good. Excellent, good job. And then finally, the last step, you are just going to simply refer to this format. So remember, it's rate of change times the variable plus initial value.
Yep.
So want to take a stab at it, how the linear function is going to look like?
We're going to see it as 0.75. I guess you would call that times t, which is the minute, plus 0.5.
Very, very good. Very excellent. Good job. Hey,
Okay. All right.
round of applause. That is it. That is the linear function. Good job.
Thanks.
We'll go ahead and stop here. How far are we on? How are we on time?
At 35 seconds.
35 seconds until
It's over.